Hello friends, in my previous video we have seen the circuit diagrams of series voltage regulator, which included the BJT based regulator and operation amplifier based regulator. Now we will be talking about shunt voltage regulator. A shunt voltage regulator is again maybe based on BJT or op-amp. So first we will be seeing the circuit based on BJT and then we will see the circuit based on op-amp. This is the general block diagram of a shunt voltage regulator. Here the control element, this is connected in shunt with the load, that is why we call it as shunt voltage regulator. So we take sample of output. Remember, the voltage regulators always have feedback from output voltage. So we take the sample of output voltage, we compare that sample with reference voltage. The comparator signal gives the signal to the control element, which in turn controls this current passing through the element and accordingly controls the output voltage. The voltage drop across this is controlled by the variation in this current through the element, which is shunt current, because it is connected in shunt, right? The output voltage of this, suppose this current is I, this is equal to I, the output voltage of this circuit is nothing but V in minus I multiplied by this series resistance RS, right? So this is the general block diagram, but let us talk about the circuit. This is the circuit which is a shunt voltage regulator based on BJT. We have a BJT connected in shunt with the load, and we have a Zener diode connected between base and this terminal, that is collector terminal or output voltage terminal. So this is basically to have a reference voltage. Here let us see the output. The output of this circuit is nothing but input voltage minus drop across this resistance, that is RS. So that is I into RS. This is the expression of output voltage. Now let us see the operation of this circuit. Here the output voltage can reduce either because of reduction in load resistance or maybe because of reduction in input voltage, maybe due to either of the regions. So when output voltage of the circuit is reduced, what will happen? Let us see. When output voltage is reduced, please see carefully, the output voltage can also be written in terms of these two voltage, this plus this must be output voltage across the load. So that is Vz plus VBE, right? So if remember, the voltage across Zener diode is fixed, this is constant, right? So if the output voltage is reduced, if this voltage reduces, this is constant, so VBE must be reduced. That means here when output voltage reduces, this is constant, so to maintain some of these two voltage at this level, so if output voltage reduces, so voltage VBE will be reduced. I repeat, if this voltage reduces, then Vz is constant, so some has to reduce, so this VBE is reduced, right? Now the collector current of BJT is nothing but I shunt, and that is equal to saturation current of BJT, this is the expression of collector current, into e raised to power VBE by thermal voltage VT. This is the expression of collector current. You can see my video on characteristic of BJT where I have discussed. So if this voltage reduces, if output reduces, this voltage is reduced. When VB reduces, I shunt is also reduced. So this current reduces when output voltage of the circuit reduces. Now please see carefully, what is current I? Current I is nothing but ISH plus I load, right? So the output voltage of this circuit I can write, that is equal to V in minus ISH plus I load multiplied by RS. So when V out is reduced, VB reduces, when VB reduces, collector current reduces, and when collector current reduces, that is your shunt current. When collector current reduces, this drop of the voltage across RS reduces. So this will reduce, and when this reduces, your output voltage will increase. So the output voltage was decreased or reduced because of reduction in load resistance, but because of this feedback mechanism, because of this control element, this current reduces, voltage drop across this reduces, which in turn pulls up the output voltage. So output voltage is again brought back to its level because of this mechanism, right? Now let us see another case. Suppose the output voltage increases, maybe because of increase in load resistance or maybe because of increase in input voltage, due to either of the regions. When output voltage is increased, when output voltage increases, this is constant. If this is constant, so this must increase. So voltage VBE increases. When voltage VBE increases, please see my collector current increases. And when collector current increases, this voltage drop will increase, and when this voltage drop increase, the difference will decrease. So that means output voltage decreases. So the output voltage which was increased because of either increase in load resistance or increase in input voltage is again brought back due to this feedback mechanism, right? So this is how the output voltage of this circuit is controlled. Fine. Now interestingly, let us see, I have this is plus, this is minus, this is current through the Zener diode. So what is power dissipation in the circuit? You may have to discuss about the power dissipation in the circuit. First of all, you please see there is a resistance connected in series with the load, so that results in losses, right? So I will be talking about the different power losses, possible losses occurring in the circuit, right? So what is the power loss in series resistance? The power loss in series resistance here in this resistance will be what? Power dissipation I will be talking about. So the power dissipation in the circuit, I will write here, the power dissipation in the circuit will be, one is because of the loss in resistance RS, that is suppose PD1. What will be power dissipation in transistor? That will be equal to voltage VCE multiplied by collector current, right? Why? Because BJT works like a linear amplifier here. So voltage drop across BJT is this, and what is this VC? VC is same as output voltage. So V out multiplied by I shunt. Similarly, what will be the power loss in your Zener diode? The power loss, the power dissipation in Zener diode will be Vz multiplied by Iz. What is Vz? Vz is V out minus VBE multiplied by current through the Zener diode. So that is how we can find the losses occurring in the Zener diode as well. There can be a small questions based on this circuit, so you should be able to handle the questions based on the shunt voltage regulator using BJT. Now we will see the shunt voltage regulator based on op-amp. In case of shunt regulator based on op-amp, we have similar circuit, but there we have op-amp instead of BJT. The operational amplifier will be used for taking the or used as comparator. Here we have BJT like this. We have a potential divider circuit on the output side like this. This is connected to ground, right? And we take output of op-amp which is connected at base terminal like this. The BJT remains connected in shunt. The only thing is the feedback mechanism is taken through a potential divider network. We have a resistance here, we have a Zener diode here. This terminal is connected at the inverting terminal of op-amp, and the non-inverting terminal is connected at the junction here. This is R2, this is R1. This is the circuit, which is the circuit of shunt voltage regulator using op-amp. This circuit, that is this potential divider network, is a sampler circuit. This sampler circuit, this is comparator. Op-amp is a comparator. We have reference voltage, this which is Vz. So this is a reference generating circuit, and this is control element which is connected in shunt with the load. So this is the circuit diagram of op-amp based shunt voltage regulator. So in op-amp based shunt voltage regulator, what do? We take sample of output voltage through this potential divider circuit. We take a reference voltage through this circuit. We have op-amp which works like a comparator, right? This is output voltage of op-amp. This is voltage VBE, same as output voltage of op-amp, and this is shunt current, right? Now let us see the operation of this circuit. That is now second circuit using op-amp. This is op-amp based shunt voltage regulator. First of all, here the point of observation is, I have, say this is terminal A, this is terminal B, this is X. So for ideal op-amp, remember we have voltage at non-inverting terminal same as voltage at inverting terminal. So the voltage at node B is same as voltage at node A, and voltage at node B is what? Vx, voltage at node X, and Va is what? Vz, right? And what is Vx? Vx, voltage at node X, is nothing but voltage across this resistance, and that voltage across this resistance can be obtained in terms of output voltage. That is simple voltage divider, R1 by R1 plus R2 into V out. So this is R1 by R1 plus R2 multiplied by V out. So we get the output voltage equal to 1 plus R2 by R1 multiplied by Vz, right? Fine. Now let us see the operation of this circuit. Here we will be taking again two cases. Case 1, decrease in the output voltage. Second, decrease in. So now let us see the operation of this op-amp based shunt voltage regulator. First, we will be taking two cases here. One is decrease in output voltage, either due to decrease in load resistance or due to decrease in input voltage, right? Second, we will be taking increase in output voltage, either due to increase in load resistance or due to increase in input voltage, right? So case 1, suppose input voltage, your output voltage is decrease, that is first case. So when output voltage reduces, what will be happening in the circuit? That is what we need to understand, or what we need to see. When output voltage reduces in this circuit, what will happen? When output voltage reduces, so voltage across R1 will reduce because the voltage across this combination has reduced. So when voltage at R1 reduces, so voltage at non-inverting terminal has reduced. And what is the differential input of op-amp? The differential input of this circuit, that is op-amp, is nothing but Vd is equal to Vx, voltage at this Vx is sometimes called as feedback voltage. This is feedback voltage, right? So this is Vx minus Vz. Voltage at this node is Vb, that is Vx. So differential input voltage of op-amp is Vx minus Vz, right? So when when output voltage reduces, so voltage across the R1 reduces. When voltage across R1 is reduced, that means voltage Vx is reduced, and when Vx reduces, so this difference will reduce. So that means voltage Vd is reduced, and we know output voltage of op-amp is nothing but open loop gain into Vd. So when the Vd reduces, output voltage will reduced, and when output voltage reduces, so what is VBE? VBE is same as output voltage of op-amp, so that means VBE is reduced. When VBE reduces, we know the collector current is here I shunt current, and that is given in terms of VB, that is V e raised to power VBE by Vt multiplied by a current which is known as saturation current. This is the expression. This expression is very important for understanding the operation of this circuit. When the voltage VBE reduces, this will reduce, that means this will reduce, right? Now let us see expression of output voltage. The expression of output voltage in this circuit is V in minus drop across this resistance, so that is Rs multiplied by I shunt plus I load. Now please see carefully, when your shunt current reduces, I have seen here, when this shunt current reduces, drop across the resistance Rs will reduce. When drop across Rs reduces, the output voltage will increase. Why? Because when this product reduces, the difference will increase. So output voltage is increased. That means when output voltage reduces because of either reduction in this resistance or maybe reduction in input voltage, that is again pulled up because of this circuit, that is feedback mechanism, right? So that is brought back at the initial level. That is case 1, when your output voltage reduces. Now let us talk about case 2. In case 2, suppose output voltage is increased. So case 1 was what? Case 1 was output voltage is reduced, and now case 2, suppose output voltage is increased. How can output voltage increase? Maybe because of increase in the load resistance, or maybe because of increase in the supply voltage. Where this supply voltage is coming from? The supply voltage is coming from unregulated power supply, right? So when output voltage increases, the drop across R1 will increase. Drop across R1 is nothing but Vx, so that means Vx is increased, and when Vx increases, this difference will increase. When this difference is increased, that means your output voltage of op-amp is increased. When output voltage of op-amp increases, that means base to emitter voltage is increased, and when base to emitter voltage is increased, that means your collector current or shunt current is increased. And when shunt current increases, the drop across this will increase and this difference will decrease, and output voltage will be brought down again at the initial value. That means that increase in output voltage is again compensated or brought down by this circuit, which is nothing but shunt voltage regulator. This is a very simple circuit but important one, so you should be able to explain the operation of this circuit. This shunt voltage regulator is not very important for competitive exams. You rarely have questions on shunt regulator, but it is important from university examination point of view and of course from understanding point of view. Let us see the example based on shunt regulator now. The transistor shunt regulator shown in the figure has a regulated output voltage of 10 volt when the input varies from 20 to 30 volt. The relevant parameters of the Zener diode and transistors are Vz equal to 9.5 volt and Vb equal to 0.5 volt, beta equal to 99. Neglect the current through resistance Rb, then maximum power dissipated in the Zener diode and transistor R. You have to find the maximum power dissipated in Zener diode and the transistor. Now, suppose current coming from supply is I, current through the Zener diode is Iz, current through the load is IL, right? Voltage across the BJT is VCE. This is IC. Current through the BJT is IC. The power dissipation in BJT is VCE into IC. Here VCE is what? VCE is equal to, that is equal to, VCE is equal to input voltage minus output voltage. Input voltage is 20 to 30 volt and output voltage is 10 volt. For maximum power dissipation, I have to take maximum power supply, input supply. So maximum power dissipation in transistor Vm will be VCE max into IC. So that is nothing but 30 minus output voltage is how much? 10 volt. So minus 10. So that is equal to 20 volt. VC is 20 volt. What is VZ? Voltage across Zener diode is VZ, right? Voltage between base and emitter is VBE. So the output voltage of the circuit is nothing but sum of VZ and VBE. Please say it carefully. Here voltage, this voltage plus voltage across RB is what? VB. So voltage VZ plus voltage across RB, that is VB. Sum of these two voltages must be equal to output voltage. So output voltage V0 is equal to VZ plus VBE. So what will be VZ? VZ will be equal to V0 minus VBE, right? And you know what is V0 is 10 volt, VB is 0.5 volt. So VZ is nothing but 9.5 volt, right? We have to find maximum power dissipated in Zener diode and transistor, right? So what is power dissipated in Zener diode? That is nothing but voltage across Zener diode into current through the Zener diode. So we have calculated VC, we have calculated VZ. Now I need to, or we need to find current through the BJT and current through the Zener diode. Now let us see how to find current through the Zener diode. Current through the Zener diode. First of all, what is current I? Current I coming from supply is nothing but V in minus V output by the resistance R. A resistance R means this resistance R. So that is nothing but I have to take maximum voltage, input voltage for maximum power dissipation. So 30 minus 10 divided by resistance R. What is the resistance value of resistance R? That is 20. So this must be equal to 1 ampere, right? Now what is current through Zener diode? That we have to find. So here we have to find collector current and current through the Zener diode. So if current through the this is neglected, if this current is neglected, then current through the base of transistor will be equal to what? IZ. It is given. The current through RB is neglected. This is given here. So IZ must be equal to what? Base current of the transistor, right? And what is the relationship between base current and your collector current? The collector current of BJT is equal to beta into base current. So my collector current will be beta into IZ. Now please see here, the current through the current from the supply I is equal to what? I is equal to Zener diode current plus collector current of BJT. Why? Because this current and this current is nothing but same as collector current. So this current coming from supply is nothing but current of the Zener diode plus collector current of BJT. So this is equal to IZ plus beta into IZ, right? Because your your collector current is what? Beta into IZ. This is what we have seen. So current I is equal to 1 plus beta into IZ. Then what will be current IZ? IZ will be equal to 1 by 1 plus beta multiplied by current I, and current I is 1 ampere. and beta is how much? Beta is given to you, that is 99. So this is 1 by 1 plus 99 multiplied by 1 ampere. So this is equal to 1 by 100 ampere, which is nothing but 10 milliampere, right? IZ is 10 milliampere. So what will be power dissipated in Zener diode? That is Vz into IZ, and Vz is how much? We have already calculated that, that is 9.5. So power dissipated in Zener diode will be 9.5 multiplied by 100 milliampere. So this is equal to 950 milliwatt or 0. That is 9, please see, that will be how much? 95. I am sorry, this will be how much? This will be, I'll make a correction here. 95 into 100 milliampere is how much? That is nothing but this is 10 milliampere, so this is 100 milliampere, not 100, sorry, 10 milliampere. So this is 95 milliampere. So power dissipation in Zener diode is 95. That is sufficient because only one option is giving me 95 milliwatt. So our answer C is correct option. However, we can find the power dissipated in transistor as well. That is nothing but VCE into, I have already written that, that is into IC. What is collector current? That is equal to beta into IB, which is nothing but beta into IZ, that I have already written here, right? This is what I have already written. So beta is 99 multiplied by collector current, multiplied by Zener diode current, so that is 10 milliampere, right? So power dissipated in transistor will be voltage VCE, which is 20 volt here. So 20 multiplied by what is the current through collector? So that is 99 into 10, that many milliwatt. So this is equal to 20 multiplied by 0.99, that many watt. You can multiply it. So that is how much? That will be nothing but you just multiply this by what is the voltage? Voltage here is VCE is what? Voltage across the capacitor, voltage across, I'm sorry, there is a correction here. Correction here is, what is voltage VCE? Voltage VCE is same as output voltage. So that output voltage, so voltage VCE, please see in the circuit, voltage VCE is same as output voltage, so that needs to be corrected here. Voltage VCE in the circuit is nothing but voltage VCE is same as output voltage, which is equal to 10 volt, right? So it has to be 10 volt, so that is a little correction here. So 10 multiplied by 0.99 is nothing but 9.9 watt. 9.9 watt is your answer, and this is the only question which appeared in GATE in 2001 from shunt voltage regulator. So now in next video we will be talking about the IC voltage regulator. So wait for my next video. Thank you very much for watching the video.
To watch more videos like this, subscribe. Click on the bell to turn on notifications. Click on the like button. Share.